Hello. Well, I thought before I put the saddle back on, whilst I can still move this tailstock all the way along the ways, I would use it to take some measurements. I haven't refurbished the tailstock yet. It doesn't really need refurbishing, but the odd thing about this tailstock is it's the only part on the lathe that is sort of grey coloured rather than Harrison beige coloured. So I speculate that it might not be from the same lathe originally. Anyway, be that as it may, I did level the lathe before taking measurements. So what I've done is I've measured from the headstock this way, and I put a mark on the ways every 5 centimetres, from 70 centimetres back to 25 centimetres. And then I'm going to put this dart-S indicator on the side slope of the V-way, measuring at right angles to the slope. And take a measurement every 5 centimetres. So this meter is 10 microns per division. So see if I can slide it along. So it goes down by 21 times 10, 210 microns in this distance of about 450 millimetres. So 210 microns is 0.2 millimetres, which is really quite a lot, isn't it? So what I'm going to do is lock the tailstock, take the reading, unlock the tailstock, move it forward to the next blue mark and repeat all the way down here, and then I'm going to switch it over to this V-way and do the same thing.
So I did that, and this is the result. I actually measured both slopes twice and took the average, because you always get a slightly different result every time you do it. I don't know quite why this kicks up at the end as it gets right close to the headstock, but it's only by a small amount. You can see that the back slope has a greater wear than the front. The back slope wear is 292 microns, front is 184. So quite a big difference there.
So assume we have a V-way as shown by this dark blue line, and resting upon it there is a saddle as shown by this purple line. So that these two surfaces are in contact, these two surfaces are in contact. And I have been measuring the extent to which this V-way is worn by measuring at right angles to its slope. And I've discovered that it's worn by a certain amount in that direction. So the question arises, if the V-way is worn in that direction by X much, by how much does this saddle come down in a vertical dimension? Well, we can calculate that. Let's assume that this line is worn by we'll exaggerate it enormously, is worn to here. So previously, let's say, these 2 points were in contact, but now this point has moved over to here. And in order to bring the saddle back into contact with that, the saddle has got to come down by an amount, let's get this right. This is a 70-degree V-way, so that angle is 35 degrees. So we want to know this distance h, by which the saddle must drop to come back into contact. That would be easy if we knew this distance, but we don't know that distance. But if we draw this triangle here, with this at right angles, this angle also will be 35 degrees. And we know this distance W because that's the amount of wear that we've just measured. So this distance, which is, we said h, so we say W over h equals sine 35 degrees. Therefore h equals W over sine 35. Shut up, you bastard. Sine 35 is 0.573, so we turn that upside down to 1.74 essentially. So h equals 1.74 times W. That's annoying because it means that the amount by which the saddle comes down is bigger than the amount by which this way has been worn as we measured it. But that's trigonometry for you. Now, of course, we haven't measured just the wear on this slope. We've also measured the wear on that slope. And both of them will have an effect on how the saddle comes down. But the effects are not additive. If you think about it, if both sides of the V-way were worn by the exact same amount, then the saddle would come down by h. If they're worn by different amounts, there will be a tendency for the saddle to rock, if it's allowed to, by the rest of the constraints on the system. So what I'm thinking is to calculate from the wear measurements I've already made how much the saddle comes down. I'll take the average of the two wear measurements and apply this formula to it.
So here are the wear figures that we measured on the front V-way, the front slope and the rear slope. The rear slope seems to be more worn, and I measured them relative to a point 700 millimeters distant from the headstock and moving back towards the headstock. So if we now average these two curves and apply the sine formula that I mentioned earlier, we can predict how much the saddle will fall in a vertical dimension as it rides along these ways. And I've done that here. This graph is on exactly the same scale as the previous one. And we see that because of dividing by sine 35, we end up with a much greater vertical movement of 414 microns. Well, now let's see whether that prediction is any good.
Right, so to test this theory, I've got this V-way which I made earlier, or a thing that sits on a V-way. If there are any of you who watched the video where I made this aluminium block, I have machined it more since then to make sure that it rests only on the worn part of this V-way and not on the top part which isn't worn. So, don't touch that, you stupid boy. This is reasonably flat here, so it doesn't matter exactly where I put it, but the idea is, and I can move it along to each one in turn. Take the measurement and so on, and then we will see by how much it goes down vertically. And so on. Right, so we'll plot those.
So, if I show those measurements, this is actually the average of two sets of measurements I took using that little aluminium saddle. You see that the prediction is not bad, but not perfect. So, that aluminium saddle in fact goes down by a worst case of 405 microns over a distance of 450 millimeters, which in old money is 10.8 thou per foot, which is not really what we want.
So what I'm thinking is that the top of this V-way is not touched by anything, and it is a machine surface, so it should be flat as it was originally. Now actually it isn't really, because if you look at it closely up here, it seems to have got rusty. So on the assumption that this surface is flat as originally machined, if I measure the height of it using this DTI mounted on the tailgate, what I'm really measuring is the extent to which the tailgate is going up and down as it moves along here on its ways. So I could take those figures and subtract them from the measurements I made before on the slopes of this V-way to get the true difference between the true amount of wear. So I'm going to do that, but I'm going to put a gauge block under here to kind of average out in case, because it's not a really totally smooth surface. And so on.
So if we add in the height of the top of the V-way onto this graph like that, that's actually the average of two sets of readings. It's not particularly smooth. And then we can subtract this red curve from the green curve to correct the green curve for the presumed movement of the tailstock, like that. Well, it gives obviously slightly better readings, a maximum vertical movement of 322 rather than what we had before, which was 405. Still not the kind of results that I would like to see.
Well, there you go. every time I take measurements on this lathe, I depress myself. I've also taken some measurements on the back flatway that the saddle sits on, but as I realised that there was a limit to the amount of punishment you could take, I haven't put them in the video. I should say that I also realised that, when I went to look at this lathe before I bought it, I should have taken some test cuts, and maybe I should have taken DTI and tried to make some measurements. The thing is, it was in such a state when I bought it that although I did look what I thought carefully at the ways, I didn't realise that they were quite as worn as they appear to be. And of course the acid test will be actually taking some test cuts when I get some power, three-phase power on this thing. And we'll see how it really performs. But I just thought, trouble is, being trained as a physicist, I can't stop measuring things. I just thought I'd measure it as best I can before I put that saddle back on in the way, which will stop me running the tailstock up and down the full length of the waist. And the other thing that's passing through my mind is that a few weeks ago I had the whole lathe apart, and I could easily have sent the bed off to have it reground. And I'm really beginning to think that I should have done that, because even if it costs a fair amount, it will be nothing compared with the cost of buying this kind of lathe today. So there you go. We live and make mistakes, perhaps.
Suppose we've got a piece of round bar in the headstock and we're looking head on at it, and it's of radius r. And suppose we decide to turn it down to a smaller radius by shoving a tool into it with a depth of cut c, so that we will be turning off this amount of material, hopefully as a chip. And the new radius will be r1. Obviously r1 equals r minus c. Now suppose that as the tool is running along this round bar, turning it off, the tool actually drops by a distance d, enormously exaggerated here, because on the theory that the saddle is running on worn ways, and so it goes down lower. That will produce a new turning radius of r2, which is greater than r1, because the tool is now further away from the centre of the part. We can calculate the value of r2 if we put these, complete that triangle. This distance is d, it's the distance the tool has dropped, and this angle is theta, let's say. Plainly, theta equals the angle whose tan is d over r1, and r2 equals d over sine theta. Hence, the taper that is cut as a result of this tool dropping as it runs along towards the headstock is r2 minus r1, which equals this thing. So let's just see what that means in terms of real numbers. Here we're assuming that the saddle falls by 0.4 millimeters, which was roughly what we measured, and that the depth of cut is 0.5 millimeter or 20 thou. The amount of taper that it cuts because of this dropping of the saddle depends upon the radius of the part. And it's worse for small radii. So we see that if the part is 10 millimeters in radius, the taper is 8 microns, or three-tenths of a thou. And for larger diameters, it's even smaller. So this is not enormously significant. Even if we double the depth of cut to say 1 millimeter or 40 thou, the taper doesn't go up much. And if we double the drop of the saddle from 0.4 millimeters, well, let's say to 1 millimeter. At that point, it starts to become significant for small part diameters.
So those considerations suggest that maybe the wear that I've measured is not going to cause too much of a problem. Of course, I have simply considered the effect of the wear in making the saddle go down. It's possible that with differential wear on the two slopes of the front V-way, that the saddle may want to go in the Y direction, that is to say the same direction as the cross slide moves, and if that were so, that would be another cause of taper. Imagine this is the saddle riding on the ways. So far we've been just considering the effect if wear in the ways as you approach the headstock causes the saddle to go down vertically, like enormously exaggerated like this. And we've discovered that it's not really very significant. But that would only happen if the front V-way and the back flat-way were worn to an equal extent. Supposing, for example, other extreme, the back flat-way is not worn at all, the front is still worn as we've found it to be, then in that case, as the tool travels towards the headstock, the height of the saddle here is going to remain the same, so what's going to happen is it's going to tilt like that. And that is a problem because it's simulating a twist in the ways. And if we imagine that mounted on the headstock there is, imagine this is the tool post and the tool sticking onto the work piece. So as we go along and this twists like this, the tool, top of the tool moves away from the workpiece. So we need to take account of that in our little calculation. And although this tilt is going to be very, very small in terms of angle, it is magnified by the distance from the pivot point, which is somewhat here, to the tool. The longer this distance is, the larger the movement of the tool in that direction as this tilt occurs. So that means this distance, of course, is roughly speaking equal to the swing of the lathe, or half the swing. So it should be more of a problem on lathes which have a big swing.
So if we imagine the workpiece here looking straight on at the chuck, and this is the tool held in the tool post, which is of height h above the saddle, and the saddle is resting on the bed on this V-way and this flat way. So if, as this whole assemblage is moving into the paper towards the headstock, if this side of it goes down because of wear, what's going to happen is as follows. It's going to rotate like that, thus moving the top of the tool both slightly downwards, but more importantly away from the centre of the workpiece. We can work out roughly how much that would be from similar triangles. W is the width of the saddle, or strictly speaking the width between the two support points, the V-way and the flat way. And if due to wear this side of it drops by an amount f, then we can calculate the amount by which the tool moves that way, which I've called A, from these similar triangles, because this angle is the same as that angle. So F over W equals A over H, and hence A equals F times H over W. So as we observed before, the effect gets worse the bigger H is, so the taller the tool is above the saddle, and it gets better the wider the saddle is. So that also makes sense on big lathes. We have big wide saddles. In the case of my lathe, the M300, if I put the appropriate figures in, and assuming that it drops because of wear by 0.3 millimeters, then you see that this effect is very pronounced, 10.4 thou movement away. So that would cause a 10.4 thou taper. And in this case, it's not dependent upon the diameter of the cut, as the previous analysis was. So this is by far the more important effect.
Right, so I've just put the saddle back on with no retaining strips. It sounds nice and smooth. I've got some oil on the ways, obviously. It sounds nice and smooth until I get up to that end. I wonder if you can listen to this. Something seems to be rubbing there. Not quite sure what that is. This is a piece of 25 millimeter diameter ground round bar, which is specified to be accurate to within half a thou, albeit only on eBay. And I think that the run out on it in the four-jaw is less than 5 microns, which is less than 0.2 thou. However, that is not necessarily the case if I move it up here. Hang on a moment, let me just clean that a bit. It's more like 0.03. Millimeters is 1.2 thou, and that is at 230 millimeters or 9 inches stick up. We measured like that. Approximately on centre height. So if I pull the saddle along here, simulating doing a cut, if you like, what's going to happen? Nothing much until we get there, and then it goes bonkers. So that is 27.27 millimeters. Essentially 0.26 millimeters over 220 millimeters, which is dire bloody bollicle. But rather what I expected. Of course, we don't absolutely know whether that problem might be caused by the headstock being tilted to the right relative to the ways. I'm not sure how I'm going to test for that. And I just tried by jacking up this side of the base to reduce that, but it only reduced it by 0.02 millimeters. In other words, from 0.27 to 0.25. So the basic problem is where in the ways, not twist in not twist. I'm thinking I'm going to have this base reground, this bed reground. Well, I don't know what I'm going to do. The measurements I've just taken are ones that I should have taken before I did anything else on this lathe when I first got it. But I'd be interested to know what anybody thinks I should do about it. I'm inclined to think that I should take the headstock off, take the bed off and send it off and have it reground if I want to have any kind of decent lathe. Anyway, thanks very much for watching.